George's Secret Key to the Universe, Chapter 26. My difficult book made simple for Annie and George, version 3. It began. What you need to know about black holes. Section 1. What is a black hole? Section 2. How is a black hole made? Section 3. How can you see a black hole? Section 4. Falling into a black hole. Section 5. Getting out of a black hole. Section 1. What is a black hole? A black hole is a region where gravity is so strong that any light that tries to escape gets dragged back. Because nothing can travel faster than light, everything else will get dragged back too. So you can fall into a black hole and never get out again. A black hole has always been thought of as the ultimate prison from which there's no escape. Falling into a black hole is like falling over the Niagara Falls. There's no way of getting back the same way you came. The edge of a black hole is called the horizon. It's like the edge of a waterfall. If you are above the edge, you can get away if you paddle fast enough, but once you pass the edge, you are doomed. As more things fall into a black hole, it gets bigger and the horizon moves farther out. It's like feeding a pig. The more you feed it, the larger it gets. Section 2. How is a black hole made? To make a black hole, you need to squash a very large amount of matter into a very small space. Then the pull of gravity will be so strong that light will be dragged back, unable to escape. One way black holes are formed is when stars that have burned up their fuel explode like giant hydrogen bombs called supernovas. The explosion will drive off in the outer layers of the star in a great expanding shell of gas, and it will push the central regions inward. If the star is more than a few times the size of our sun, a black hole will form. Much larger black holes are formed inside clusters in the center of galaxies. These regions will contain black holes and neutron stars, as well as ordinary stars. Collisions between black holes and the other objects will produce a growing black hole that swallows anything that comes too near it. Our own galaxy, the Milky Way, has at its center a black hole several million times the mass of our sun. Okay, we're going to skip page 234 and 235. We'll come back to that. Section 3. How can you see a black hole? The answer is you can't, because no light can get out of a black hole. It's like looking for a black cat in a black cellar. But you can detect a black hole by the way its gravity pulls on other things. We see stars that are orbiting somewhere, but we can't see, but that we know can only be a black hole. We also see disks of gas and dust floating around the central object that we can't see, but that we know can only be a black hole. Section 4. Falling into a black hole. You can fall into a black hole just as if you can fall into the sun. If you fall in feet first, your feet will be nearer to the black hole than your head, and you will be pulled harder by the gravity of the black hole, so you will be stretched out lengthwise and squashed in sideways. This stretching and squeezing is weaker the bigger the black hole is. If you fall into a black hole made by a star only a few times the size of our sun, you will be torn apart and made into spaghetti before you even reach the black hole. But if you fall into a much bigger black hole, you will pass the horizon, the edge of the black hole, and the point of no return, without noticing anything particular. However, someone watching you fall from a distance will never see you cross the horizon because gravity warps time and space near a black hole. To them, you will appear to slow down as you approach the horizon and get dimmer and dimmer. You get dimmer because the light you send out takes longer and longer to get away from the black hole. If you cross the horizon at 11 o'clock, according to your wristwatch, someone looking at you would see the watch slow down and never quite reach 11 o'clock. Section 5. Getting out of a black hole. People used to think nothing could ever get out of a black hole. After all, that's why they were called black holes. Anything that fell into a black hole was thought to be lost and gone forever. Black holes would last until the end of time. They were eternal prisons from which there was no hope of escape. But then it was discovered that this picture wasn't quite right. Tiny fluctuations in space and time meant that black holes couldn't be the perfect trap they were once thought. Instead, they would slowly leak particles in the form of Hawking radiation. The rate of leakage is slower the bigger the black hole is. Hawking radiation could cause black holes to gradually evaporate. The rate of evaporation will be very slow at first, but it will speed up as the black hole gets smaller. Eventually, after billions and billions of years, the black hole will disappear. So black holes aren't eternal prisons after all. But what about their prisoners, the things that made the black hole or that fell in later? They will be recycled into energy and particles. But if you examine what comes out of the black hole very carefully, you can reconstruct what was inside. So the memory of what falls into a black hole is not lost forever, just for a very long time. You can get out of a black hole. Okay, turn back to those two informational pages on 234 and 235. Neutron stars. When stars much more massive than the sun run out of fuel, they usually expel all their outer layers in a giant explosion called a supernova. Such an explosion is so powerful and bright it can outshine the light of billions and billions of stars put together. But sometimes not everything is expelled in such an explosion. Sometimes the core of the star can remain behind as a ball. After the supernova explosion, this remnant is very hot, around 180,000 degrees Fahrenheit. But there is no more nuclear reaction to keep it hot. Some remnants are so massive that under the influence of gravity, they collapse in on themselves until they are only a few dozen miles across. For this to happen, the remnants need to have a mass that is between around 1.4 and 2.1 times the mass of the sun. The pressure is so intense inside these balls that they become liquid inside, surrounded by a solid crust about 1 mile thick. The liquid is made of particles that normally remain inside the core of the atoms, the neutrons, so these balls are called neutron stars. There are also other particles inside neutron stars, but they really consist mostly of neutrons. To create such a liquid on Earth is beyond our present technology. Stars like the sun do not explode in supernovas, but become red giants whose remnants are not massive enough to shrink under their own gravity. These remnants are called white dwarfs. White dwarfs cool down over a period of billions of years until they are not hot anymore. Many neutron stars have been observed by modern telescopes. Since the cores of the stars are made of the heaviest elements forged inside stars, like iron, although white dwarfs can be quite small, about the size of Earth, they are extremely heavy, about the mass of the sun. Star remnants that are less heavy than 1.4 times the mass of the sun become white dwarfs. Neutron stars are born from supernovae remnants that have between 1.4 and 2.1 times the mass of the sun. Remnants more massive than 2.1 times of the sun never stop collapsing in on themselves and become black holes.